Assalamualaikum warahmatullahi wabarakatuh. My name is Nick Fazarul Hakim bin Kamal Zuki and my metric number is CD240138. Today I want to present about our group project thermodynamic, which is fundamental of steady flow devices, which is turbines. So now we go to the 1.0, which is introduction. Okay, the turbine contributes to more efficient energy conversion, making it a crucial component of the energy system. The ability of turbines to transform high pressure steam or gas into mechanical energy makes them indispensable for industrial applications such as power generation and aviation propulsion. In order to attain a high degree of optimal performance, both the design and methods of operation are crucial. Okay, next we go to 2.0, which is background and theory. Okay, so the turbines are machines that convert the energy of a moving fluid like steam, water, or gas into mechanical energy, which is often used to generate electricity. They are steady flow devices, meaning the fluid flows through them continuously. As high pressure fluid enters the turbine and passes over its blades, the blades spin, producing useful work. This process follows the first law of thermodynamics, where the energy from the fluid is turned into mechanical energy. Turbines are widely used in power plants, jet engines, and hydroelectric dams for efficient energy conversion.
Okay, so this group case study discusses a steady state flow device, or we call SSFD, specifically a gas turbine in a flight system. A gas turbine is a continuous flow inertial combustion engine that converts the chemical energy of fuel into mechanical energy to propel an aircraft. Its main components include power producing section or gas generator, and its design is adapted for various applications such as marine, land, or air use. In aviation, gas turbines play a crucial role as the primary source of thrust. The gas turbine system starts with ambient air intake, which is compressed by the compressor. Fuel is then added and ignited in the combustion chamber, producing a high energy exhaust flow. This flow rotates the turbine, which drives the propeller and propels the aircraft forward. The main component of the system are the compressor, combustion chamber, and the turbine. Gas turbine use various types of fuel and operate under steady flow condition with pressure and temperature decreasing from high to low.
Hello, my name is Muhammad Azmuddin. Today I will present about analysis of the SSFD's performance in the case study. Steady airflow is essential in flight systems because it allows air to move smoothly through critical components like wings, engines, and control surface, ensuring stable, efficient, and safe operation. In gas turbine engines, this steady flow supports a continuous cycle of compression, combustion, and expansion, where fuel energy is converted into mechanical power to produce thrust or drive a fan. Engineers can adjust each stage of the cycle to improve performance and reliability. A key part of this process is monitoring energy changes, especially the drop in enthalpy, which indicates that the air has done useful work, such as turning the turbine blades. By measuring how much enthalpy decrease, we can determine the engine's work output and overall efficiency. Now I will present about the analysis of the SSFD's performance in case study of change in parameter 1, In this case study, we analyze the performance of a steady flow, steady state device, specifically a gas turbine where high pressure air enters at 1200 K and exits at 660 K in an adiabatic process. Our goal is to calculate the work output per unit mass of air using temperature-dependent enthalpy values. The general energy balance for steady flow system shows that energy entering equals energy leaving, and it includes terms of heat, work, enthalpy, kinetic and potential energy. However, because this turbine operates adiabatically with negligible change in velocity and elevation, the equation simplifies to W dot out equal to m dot times h1 minus h2. This means the work done by the turbine depends only on the drop in enthalpy from inlet to outlet. By using accurate enthalpy values at these temperatures, we can determine how much useful work is produced, which reflects the efficiency of the turbine. To complete the analysis, we use values from the air property tables to calculate the work done per unit mass. At the turbine inlet temperature of 1200 K, the specific enthalpy H1 is 1277.79 kJ per kilogram, and at the outlet temperature of 660 K, H2 is 670.47 kJ per kilogram. Using the simplified energy equation, W out equal to H1 minus H2, we subtract the two enthalpy values to get the work output. W out equal to 1277.79 minus 670.47 equal to 607.32 kJ per kilogram. This result shows the amount of energy converted into useful mechanical work for every kilogram of air passing through the turbine, which helps us evaluate the efficiency and performance of the system under the given temperature conditions. Now I will explain about change in parameter 2. This explains the performance analysis of a steady-state flow device, specifically an aircraft gas turbine. The problem involves high pressure air entering the turbine at 1300 K and exiting adiabatically at 300 K, with the objective to determine the work done per unit mass using temperature-dependent properties. The foundational principle for solving this is the conservation of mass and energy for steady flow processes, while the general steady flow energy equation is comprehensive. For this specific adiabatic turbine, it simplifies significantly, neglecting change in kinetic and potential energy, and with no heat transfer, the work output per unit mass is simply the difference in enthalpy between the inlet and outlet states. W out equal to H1 minus H2. Therefore, the next crucial step is to find the enthalpy values of air at 1300 K and 300 K to calculate the work done. This slide details the calculation of work done per unit mass for the adiabatic gas turbine, utilizing the simplified energy balance equation. W out equal to H1 minus H2. The necessary enthalpy values were directly obtained from air property tables, table A17. At the inlet temperature of 1300 K, the enthalpy H1 was found to be 1395.97 kJ per kilogram, and at the outlet temperature of 300 K, H2 was 300.19 kJ per kilogram. Substituting these values into the equation, the work done per unit mass by the turbine was calculated as 1395.97 minus 300.19 equal to 1095.78 kJ per kilogram, confirming the turbine's work production. Now I will present about discussion and comparison. From the earlier calculation, we can see that the gas turbine operates under steady flow conditions, meaning the air moves smoothly and consistently through the system. Even with a large energy drop, as long as it happens steadily over time, the flow remains steady. This energy drop, known as enthalpy loss, represents useful work being done, like spinning the turbine blades. The bigger the drop, the more work is produced. In a gas turbine engine, the turbine has two main roles: to drive the propeller and to supply power to other components like the compressor. The compressor draws in large amounts of air and increases its pressure and temperature. Using energy from the turbine operates by expanding hot, high-pressure gases that spin the blades and generate mechanical energy. Since air naturally flows from high to low pressure, the turbine blades are carefully shaped to guide this flow efficiently. For the system to work at its best, all the air must pass smoothly through the turbines, blades, ensuring effective energy conversion and engine performance. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fehman bin Mamlukman and my matrix number is CD240095. And I will be continuing presenting about discussion of results. So let's go through this. In this section, we analyze how gas turbines perform under different temperature drops using steady flow assumptions. So for case 1, when the temperature dropped from 1200 Kelvin to 660 Kelvin, the turbine produced 607.32 kilojoules per kilogram of work. But in case 2, with a greater drop from 1300 Kelvin to 300 Kelvin, the work output is much higher, which is 1095.78 kilojoule per kilogram. This shows that a larger temperature drop gives more energy for the turbine to convert into useful work. It's consistent with the first law of thermodynamics, which states that the decrease in internal energy or enthalpy becomes work output in an iterative process. So that's all from me. Thank you very much.
Assalamu alaikum warahmatullahi wabarakatuh. Hello, my name is Warsame Abdurrahman Hassan. My metric is BD230011. In this part of the presentation, I'll be explaining the conclusion of our topic on steady flow devices. So to conclude our presentation on steady flow devices, we explored the role of turbines in geothermal energy systems. Okay. So geothermal energy captures the Earth's internal heat. Okay, geothermal energy captures the Earth's internal heat and converts it into usable power. Okay, so this heat is extracted from underground reservoirs, and used to produce steam, which drives turbines to generate electricity. So in this setup, turbines function as steady flow devices, meaning that they might operate under stable. Okay, they will operate under stable conditions, while continuously converting thermal energy into mechanical work. So unlike fossil fuels, geothermal energy is renewable, reliable, and environmentally friendly. It provides consistent power output, make it an ideal based load on energy. Okay, load on energy. And also like source in regions with accessible geothermal resources. So by studying turbines as steady flow devices, we understand how vital they are in harnessing clean energy efficiently. Their application in the geothermal system highlights how thermodynamics principles are used in real-world engineering, okay, to support our global efforts toward sustainability and energy. Okay, energy transition. Thank you for listening. Assalamu alaikum. Hello everyone, my name is Abdurrahman Hassan. My military is BD 230011, and in the group presentation I'll be explaining about the reference part we use for research for our project. So this is an explanation for all the 5 references we used. So for our thermodynamics group project titled The Fundamentals of Steady Flow Devices Turbines. To make sure our report was accurate and reliable, we used 5 main textbooks, okay? First was the Sengel and Bose, okay? Sengel and Bose Thermodynamics and Engineering Approach 9th edition gives us a strong understanding of the first law of thermodynamics, especially for open systems like turbines, okay? For especially open systems like turbines. The second reference, Moran and Shabiro's Fundamental of Engineering Thermodynamics 9th edition, was helped us with the performance analysis and isotropic efficiency of turbines. The third reference we used Sontag, Borgnake, and Van der Waals Fundamentals of Thermodynamics. Okay, Van Waals Fundamentals of Thermodynamics 6th edition to support our theory in energy flow or on energy flow. Okay, and control volume analysis. Next one is E-Stop, and Isom and McConkey's Applied Thermodynamics 5th edition. Provided a practical turbines example like that are used in the industry. Okay, that is used in industry. Finally, the Sengel and Kimbal's Fluid Mechanics 3rd edition support our study of fluid behaviors in turbines. So that's about the references. These references were textbook based and properly cited. Thank you for listening.